Hello everyone. Now we're going to look at an application of the derivative called related rates. And a related rates problem is pretty self-explanatory because it occurs when a rate is related to one or more other rates. And that usually depends on the geometry of the system that you're dealing with. For this example, we have two different masses of some kind, one on the negative x-axis initially and it's moving to the right at some velocity, and another on the negative y-axis and it's moving upward at some velocity. These could be particles moving through space, these could be cars approaching an intersection, but what we ultimately want to find is the rate at which the distance between them is decreasing. And so we need an equation that relates these distances to the rates at which they're changing. And so the geometry for this example is pretty straightforward. It's a right triangle, so we want to use the Pythagorean theorem, written right here. And to relate these distances to their rates, we want to take the derivative. So we take the derivative of this whole equation with respect to time, because that is what these distances are changing with, because this is moving at a velocity, which is distance over time. So taking this whole derivative implicitly, we get 2x times dx dt plus 2y times dy dt is equal to 2z times dz dt. And now, this doesn't look like something we can work with maybe at first if you're not very experienced, but dx dt and dy dt are actually known values. Dx dt is the derivative of the position in the x direction with respect to time, or the velocity in the x direction with respect to time, or not with respect to time, and dy dt is the velocity in the y direction. It's the rate at which the distance y is changing. So these are known values, and we can plug all of our initial values in here and solve for dz dt, which is the rate at which z is changing. So let's do that. Actually, the first thing we can do here is cancel out all these 2's. So we just have x dx dt plus y dy dt equals z dz dt. And plugging in our initial x position, we have minus 15 and times velocity in the x direction, 7.5, and plus initial y position, minus 10, and velocity in the y direction, which is 5, is equal to z, and the initial distance between these 2 points I already calculated because it's just using the Pythagorean theorem. It's 18.03 meters. So 18.03 times dc dt, which is what we want to solve for. Okay, so let me grab a calculator. Alright, minus 15 times 7.5 plus minus 10, 5. That is, this side here is minus 48.875. Yep. And that equals, 18.03 all times dz dt. So that divided by, that divided by 18.03, we get dz dt, or the rate at which the distance between our two objects are changing, is equal to minus 2.71 meters per second. And there it is.